And we come to the next session, and we have Maurizio, who will tell us more about what the state of the development is for SEEIST.
Thank you, host. Thank you, Minister, for the invitation. And we wait for the slides.
Okay. So you have 20 minutes maximum.
I was
25.
25. I mean, don't
25, sorry.
You tell the people that's my budget. Now don't cut me my time.
I will cut both.
Okay, thank you. So, okay, this is my first slide. Just to show you that I fully agree with Marco.
Yes,
I fully agree with Marco when he said that the next breakthrough will come from biology, but the price tag for it will come from physics. Because if we look at the size, so we want to put the patient and the scientific research at the focus of the new facility, but you see the patient is very small there, and behind this is an image from Heidelberg. It's a huge accelerator complex. If you look at the document of for SEEIST prepared in 2018, 75%, more than 75% of the cost of the facility, it comes from the machine. And also more than 75% of the operation costs are related to accelerator. So it's a big challenge to make an accelerator that will make the cost lower and the operation simpler for a new facility. Now, I also have to thank Sandro Rossi because he explained to you very well, in very simple words, how an accelerator works. So I don't need to go into any more details. I only have to mention that this is the standard layout for an accelerating system, an ion source, a linear injector, or a synchrotron, but there are other ideas on how to make a facility, for example, making a long LINAC going all the way up to the maximum energy. So, but there are different layouts of accelerators that are interesting for us. And we have also to observe that Europe has always played a leading role in the development of therapy facilities. So we have now in Europe 4 facilities operating, doing ion therapy. I will concentrate only on ion therapy, so no proton therapy. Ion machines can also make protons, but the future, as we have seen from the presentations this morning, is really for ion therapy, ion machines. There are 2 facilities that are based on a design of the so-called PIMS, so design that was started in '96, first patient treated now in 2011, and then 2 machines are based on the GSI's Siemens design that was started at GSI in '98, first patient at Heidelberg in 2009. Now, it's about 20 years from the time when these machines have been designed. There was a lot of progress in the field of particle accelerators, and there are many more new technologies that have appeared in the field of accelerators. So the first question is, should we really continue and build a 5th facility in Europe with the same design, or should we really try to go beyond and see how we can apply the latest technologies to ion therapy accelerators? So where should we start from? The original SEEIST report of 2018 is an excellent starting point. So it's a perfect description of the most modern design that you can have based on the so-called PIMS layout. So it's a very complete work that came out to a machine with a cost of 120 millions, operation cost 11 millions per year, and a footprint all included of 15,000 square meters. So this design has the advantage of being there, of being immediately available if you want to start the construction tomorrow, but might suffer of similar problems as the present generation of ion therapy machines. Can we really think of going beyond this design? Of course, you know what is my answer. Yes, we have to do it, but how? What are the parameters? What are the specifications for a new design? Last year, in June 2018, we made an interesting workshop where we have called representatives from the medical community and from the medical physics community to tell us what are their requirements, what do they really want from a new machine. And of course, some of the requirements are, in a sense, obvious. Lower cost. These machines are very expensive, so make it cheaper. Reduce footprint, make it smaller. Smaller also means that it is really easier to reproduce. and a design that can be replicated in other places. Lower running costs, of course, and also be faster dose delivery, and this means more intensity. This is one of the big challenges for the accelerator designers. Give us more intensity, more particles into your machine. Then, of course, a rotating entry, as those that we have seen for some of the existing centers, is considered as a must by the medical community. They really want to have the precision to position the beam on the patient that is provided by a gantry. And then use of multiple ions. So these are requirements that are very general coming from the medical community. And if you build a machine in the Southeast Europe, there are some additional requirements that also something should be easy industrialized, should really be able to involve industry in the construction. This is a very important point. It is important everywhere, but particularly, I think, to grow this region. Then reliability is operation, and built in acceptable time. You cannot wait for 10, 20 years to build a machine, and with reduced technical risk. So we can do something new, and an innovative design also has many advantages because it can attract more support than replicating an old design. So CERN, for example, is in only because there is something challenging. There is a challenge of a new design where really we can apply new technologies. And this also is very attractive to other institutes, as we will see, from Europe and in particular from the region. But what type of machine can we build? So what should be this new design? What are the options? So for the moment, we have considered 3 options. The first is a synchrotron with conventional warm magnets that is similar in the magnet design to the previous facilities, but has many innovative features, including a factor 10 higher current than Heidelberg-Knoop or the present facilities. And this has a lot of technical requirements on our side, so we have to develop a new linear injector at higher energy. We have to inject multiple turns. We have to pile up particles in the synchrotron from different pulses in the LINAC, multi-turn injection. And so to reach this factor of 10 in intensity, we can work to have different extractions to allow modalities like the flash therapy that has been shown this morning possible in this new facility. So you have to couple a conventional slow extraction like in all present accelerator centers with faster extraction. So there are a number of improvements that one can make with respect to the present machines, even keeping the limitation given by standard magnets. But the big advantage would be to go to superconducting magnets. Superconducting magnets, you see that in the center you have a scheme where you have only 4 magnets that bend the beam by 90 degrees. It's kind of a square, no longer a ring, in fact. And if you look at the circumference, the size is about a factor of 3 lower, thanks to the higher fields that you can reach in a superconducting machine. And the cost also is considerably lower, thanks to the fact that you have less components, shorter distances, and you save quite a lot of money in real estate in the cost of the building, thanks to superconductivity. We have also explored a third option, which is going to the LINAC, using the LINAC to go to the final energy. You can build a high-frequency LINAC that goes to the full 430 milli per unit. So the third image shows how this LINAC looks like. It's not a scale, unfortunately, but it is about a size similar to the superconducting synchrotron and a similar cost, more or less. So 3 options for the accelerator and 2 options for the gantry. For the gantry, also nowadays, a gantry, if in Europe is built a new gantry, it must be superconducting. For the gantry, there is no, let's say, other option. You have to go superconducting. You have to profit of the advantage of superconductivity, either with a conventional rotational gantry, the first image. So this is a scheme that comes from the Terra team for a gantry equipped with superconducting magnets that rotates by slightly more than 180 degrees, where you can simply move the patient by 180 degrees. You save in the range of movement of the gantry, and it's a promising idea. But this has to be compared to other modern ideas using superconductivity, of gantries where nothing moves, not the patient, not the mechanical structure, but only you move around your beam using a little magnet inside a toroid. So this is a scheme of a toroid that can deflect the beam directly on the patient in the position that the doctors want. So this is also two promising ideas, but they have to be explored. We have to take some decisions and see which one is the most interesting. Okay, apart from the gantry, we made an analysis of what are different features of the accelerator designs. And we compared warm synchrotron, superconducting synchrotron, and linear accelerator in terms of construction cost, operation cost, footprint, performance, time to development, risk of development, and treatment protocols. We don't have yet all the numbers. We want to replace the colors in this table with the numbers, and it is ongoing. But for the moment, what I have are colors to give some ideas that, of course, a warm synchrotron is the fastest in terms of as the lower time to development and risk. You can use the existing treatment protocols, but still keeps a construction cost which is the same ballpark that you have seen from the previous proposal, and also operation cost and footprint are within what is standard nowadays. With a superconducting synchrotron, of course, you gain in cost, you gain a lot in operation cost and footprint. Performance is always good because this comparison is done with the higher intensity that we want to have into the machine, but more time to develop is needed, and there is, of course, some technical risk in developing the new superconducting magnets. The linear accelerator is the best in terms of performance. Is also relatively, so to be confirmed at lower construction cost, lower footprint, but time to development is going to be much longer and very likely with more risks. And also for linear accelerator, one has to develop completely different treatment protocols. And all the license is going to take more time. So what we have decided is that just to take out the LINAC option and concentrate on these two synchrotron options for the future. And this is now what we propose, the strategy for the future SEEIST machine. So in the future now, we are going to work on two designs. One which is an intermediate design, which is innovative, can be built relatively quickly, and then something that it is for with a longer development time, the full superconducting version. These two designs differ only for the type of magnets that are used. The first machine, the warm machine, is already very innovative because it will have 10 to the 10 carbon ions per pulse. The standard now is about 10 to the 9. It will have fast flow extraction, will be equipped with a LINAC of new design up to a higher energy, and will have, you see, a superconducting gantry at the end and operate with multiple ions. The second design keeps all the advantages of the previous design, but on top of that, it is much smaller and possibly less expensive, thanks to superconductivity. To this design, this design has in common the intensity, the beam parameters, and in particular, with 10 to the 10 carbon ion per pulse, this would be the world record in beam current for a therapy facility. On top of that, what we want with these designs is to keep the additional features of something which is upgradable. So it is always possible to start with a beginning with only experimental rooms and using only the fast flow extraction, and then in a later stage add the superconducting gantry. We should not be afraid of superconductivity. Superconductivity is now the key to modern particle accelerators, and it is what has allowed the main progress in the past, in the last generation of accelerators. It's a reliable technology. At CERN, we operate the superconducting magnets of the 1400 superconducting magnets of the LHC in a very reliable way. In a sense, it is more solid, I believe, as a technology. There are less battles to play with. So just a superconducting magnet is something which is more compact than a standard magnet, and in a sense, it's something that requires some time to be built, but it's very reliable. And one of the ideas for this new superconducting machine would be to use a new type of design of superconducting magnet, which is coming from Berkeley, that you see here, the so-called canted cosine theta magnets, which are quite special in a sense, and would open really new perspectives, not only for the SEEIST facility, but also for other applications of particle accelerators. So our strategy is based on two phases. So first of all, now what we celebrate today is the start of the design phase via the DLR service contract that aims at comparing the three options, not only in a qualitative way, as I've shown in my previous slides, but also in a quantitative way, and really identify what is the right direction for the design. In a sense, we have done this work already because we have made our choice of focusing on the synchrotron in the two blends of warm design and superconducting design. And then the next stage, the phase 2, will start, we hope, with another celebration in Montenegro next year, when we start the HITRI design study. And this corresponds to an application that we are just preparing now for support from the European Commission Research Infrastructures for the phase 2 that should go from September 2020 to August 2023, where we developed the main features of the designs that you have seen. This design study, you've seen already in the presentation this morning, is called HITRI, Heavy Ion Therapy and Research Infrastructure. It's a project that will last 3 years. The proposal includes 9 work packages. You see a lot of institutes contributing from Europe and from Southeast Europe, particularly for this region. There are at the moment 13 participants from Central West Europe and 7 participants from Southeast Europe, including the SEEIST. The coordination the overall coordination of the project is going to be done by CERN. CERN will take care of the administrative coordination, but the scientific coordination will be fully with SEEIST, and Minister Demianovic has agreed to be the coordinator for the design study with the support of Nicolas Sammut for the University of Malta, who is going to be the deputy coordinator. This project will focus on the technical aspects and on building community and capacity, which is the main challenge. While it will leave out political and organizational aspects specific to SEEIST that will be approached by SEEIST activities that will go on in parallel with this design study. So this is about the timeline. So at the moment, we are concentrating on the first phase, where we have support from the European Union via the DLR and support from CERN. NIMS is the Next Ion Therapy Medical Machine Study, which is the CERN initiative for the next generation of ion therapy machines. And this will produce a conceptual design report for the 3 designs that we have seen. The next step will be to have all the information ready to prepare a technical design report or a pre-technical design report for a warm machine in 2021, and then 2023, at the end of the design study, we will have all the elements to produce a technical design report for the superconducting machine. There is something which is very important in this design study, the fact that the goal is to create a community around the SEEIST project. Something that also I liked a lot was a slide by Sandro Rossi that pointed out how an important point for the construction of CNAO was to collect a community around the project that could help to build the project, and then was available for consultancy, for advice after the construction, but would leave a space to young people that will have to operate the machine. So this is something which is very important, I think, at this moment, is to create a community around the SEEIST. And this project is an exceptional tool to create this community and to contribute to build in the region the competencies that are required to build a facility. What we want is that in every work package of this new project, phase 2 of HITRI, we want to have at least 1 institute from the region. And this is a way to transfer the competencies and grow the competencies in the region. On top of that, we don't have to forget industry, because these kind of projects are an excellent tool to develop industry, to develop technologies in the region and with the region, And in fact, we must aim for a virtuous system where you have really a collaboration between European accelerator centers, local university research centers, and industry. Industry from the region, from outside of the region, and with SEEIST in the middle. And already a step in this direction is a workshop that we are organizing in Sarajevo in early April that we call SEEIST Meets Industry. And we have to thank Professor Milosevic for the University of Sarajevo, who is the local host and organizer of this meeting. And this will be an exceptional opportunity to present the technology possibilities of the project to the industry, hoping to attract interest and possibly joint ventures with Western European companies that will support the construction of the machine. So now I come to my last slide. And I think that we have to underline two very important points. The first is that for us, the goal is really more creating a community than building an accelerator. We have to create a community to grow a culture in the region, which is a goal which goes beyond building a particular accelerator. And this for us is one of the main challenges. And second, we have to decide whether the SEEIST accelerator is going to be the last one of the first generation or the first of the new. And of course, you know what is my suggestion, what is my answer. Yes. And also you have to underline that to build something which is at the forefront of technology is not a limitation, on the contrary, it's an opportunity. It's an opportunity because it's the best way to attract the interest of young people, the interest of the institutes in the area, the interest of industry for something that has a future in terms of technology that goes beyond the immediate need of the SEEIST. So, and we have to we have to be very flexible, have a flexible strategy to maximize the result and to minimize the risk of the project. And if I can finish with the message, so I believe that our goal for our accelerator people, but also for this project, is not to plant a tree, but to grow a tree in the region. Okay, thank you for your attention.
Optimistic. So I appreciate your approach.
I have the more optimistic I am. So
yeah, okay, good. One question. Otherwise, we are a bit late in the program, and maybe we should ask now to get the next talk, which is on the agenda, from Professor Gershal from the North Macedonia. Okay. So thank you to tell us about the building community in the region. Okay.
Thank you, Chairman.
Thank you.
Firstly, I would like to thank the organizer for kind invitation and this opportunity to present an overview about the availability of imaging and radiotherapy equipment in the South Europe, and from future back to the Southeast Europe. So the content of this short presentation is availability of medical technology, imaging equipment, use of imaging equipment, radiotherapy treatment equipment, and cancer statistics, incidence mortality ratio. This is the list of countries which belongs geographically to the region of Southeast Europe. The data for this presentation were taken from the Eurostat database, mostly, and I have to say that it was quite challenging to provide reliable data for Bosnia and Herzegovina, Kosovo, and for Montenegro. So, imaging equipment, the data from 2015, the data for North Macedonia were 2018. This is the number of computed tomography scanners per 100,000 populations. As you can see that in Southeast European region, the most scanners are 3.5. There are in Greece and Bulgaria, the least 0.8 in Albania, in average 1.7 scanner per that population. In Europe, the highest number of scanners there are in Denmark and Switzerland, the least in Hungary, and in average 2.3. As you can see, that in Southeast European region, there are 24% less CT scanners for the same population. Magnetic resonance imaging MRI units. In Southeast Europe, the most are in Greece, 2.4, the least in Albania, in average 0.8. In Europe, the most 3.4 in Germany, the least in Hungary again, and in average 1.5. As you can see, 43% less there are MRI scanners in this region. I'm not talking about the performance of the scanners, the protocols that have been applied during examination of patients, just about the core number about the machines. Gamma cameras in this group are included also SPECT CTs. In Southeast Europe, the most are in Greece, 1.4, the least again in Albania, in average 0.52. In Europe, the most gamma camera are in Belgium, the least in Estonia, and 37% less availability of gamma camera, nuclear medicine. PET scanners, the most in Macedonia, 0.2, North Macedonia, 0.2, sorry, the least in Albania, and in Europe, the most in Denmark, the least in Latvia and Cyprus, and 55% less availability of PET scanners, PET CT in this region. Then I put several slides that describe the usage of these imaging modalities. The number of CT scans, I couldn't find data for Albania and Greece. The highest number of CT examinations have been done in Turkey, but the strange is that in Turkey there are 3 times less CT scanners, and I was wondering about the heavy workload of that scanner there. The list in Romania, in average 7,952. In Europe, the most number of CT scans are performed in Luxembourg, Belgium, and France, the least in UK. Not only the number is the slowest, but also I know that the doses are the lowest in UK during the one CT scanner. In the average, 12,825. So also I would like to say that it was quite difficult to provide data for private hospitals units. It's, for example, in North Macedonia, it's quite impossible to have data from private hospitals, how many scans they have done, MRI, CT, whatever it is. Number of MRI scans, no data for Albania and Greece. The most number of CT scans in Turkey, again, but 3 times less MRI machines. The least in Bulgaria. In Europe, the most in Germany, the least in Cyprus, Portugal, Hungary, and Finland. So again, the same story about the number of private units. So this is a very good and reliable indicator, the number of MRI scans versus number of CT scans, which indicate having of good clinical pathways protocols for diagnostic or follow-up for the patients. And no data for Albania and Greece. The highest ratio goes in favor to Turkey, the lowest ratio in Bulgaria. That means the highest proportion of CT scans have been done in Bulgaria in comparison to MRI. North Macedonia, something in the middle. The highest ratio in Europe, Liechtenstein, Finland, and Germany, the lowest in Cyprus. So as you can see, about 3 times less MRI exams have been performed in Southeast Europe in comparison to the rest of Europe. This is not only due to lack of number of MRI scans, also due to using simple different type of protocols for examination of patients. Number of PET scans, no data from Albania and Greece. The most PET scans in Turkey, the least in North Macedonia. Although there was a highest number of PET scanners, but this year there is a dramatically improvement in the number of patients that were examined by PET methodology in North Macedonia. No data from Belgium, and the most PET CT scanner have done in Denmark, and the least in Lithuania. So, oops. A few slides about the therapy equipment. Any type of radiotherapy equipment, Linac, Cobalt, if there is something such equipment. So in Southeast European region, the most radiotherapy equipment there are in Bulgaria, the least in Albania. In Europe, the most in Belgium, the least in Estonia and Liechtenstein. And in average, 38% less equipment in this region. Again, I would like to point out that I don't talk about the performance of that equipment. This is very interesting from my point of view. On the graph represented the tendency between 2010 and 2015 about the number of available radiotherapy equipment, and the highest increasing number of radiotherapy equipment was noticed in Croatia, Belgium, Lithuania, and Bulgaria. But according to the available data in Eurostat, there was a decreasing of number of radiotherapy equipment in Germany and Switzerland in this period of time, maybe due to building of new radiotherapy facility, I don't know. And this was quite tough to prepare this slide for this presentation. I have gone through bulk of literature and different percentage numbers of incidence, mortality for this region. And I decided to choose mortality incidence ratio as an indicator of cancer management outcomes. This slide, Minister Sanja Damjanovic presented this morning. And it's clear that the highest mortality incidence ratio is in Bosnia and Herzegovina, Albania, North Macedonia, Montenegro, and Greece, the lowest in Slovenia. And in Europe, the highest ratio mortality incidence is in Hungary and Lithuania, the lowest in the Norway, Sweden, and Switzerland. Well, this is not very reliable data because there is no cancer registry in the most of Southeast European countries, and very often heart lung failure is declared as a cause of death in cancer patients. The exception is Slovenia. They have a very good, for a long time, decades, cancer registry. And less imaging and treatment equipment is only one factor for higher mortality incidence ratio. There is not good screening program in this region, screening in general, not only for breast screening, colon screening, etc. Not very good protocols for diagnostic and treatment, follow-up of patients, etc., etc. There are plenty of questions regarding from diagnostic to the final outcome of this type of patients. So there are the references, and thank you for your attention. Wow.
One has to continue to improve the quality of the data to be sure that it's not giving wrong messages. Yes, there's one question I see.
The mortality versus the mortality versus incidence ratio says something about how well a country deals with it. However, the incident ratio in itself, normalized to the population, would be extremely interesting.
So it's the next task.
But
My
I
answer-
suppose you have that in your data. You have not shown it, but it's a question to you.
Oh, okay, so I would say I'm
You
a
have a plot
physicist.
on the incidence ratio.
I am a physicist. And as a physicist, I could find this data. I'm not a
She did not do
oncologist
this.
or
So
epidemiologist.
it was not, it is not in her data yet to show, but maybe we should improve and see what has to be done. I have another question there, which I cannot avoid to. 10 questions. Was the same question. Okay, so GSI has the same questions. Good. Manjit, you are anyway the next speaker.
I'm not going to be the next speaker anyway, but we know this is a challenge, and that's one of the things we need to make sure that happens. Okay, and I'll put that up. Just a sec.
So it's your turn
Yeah.
anyway. Thank you very much. Okay, so you continue to work on this data, and Manjit is now on the agenda. Please. Give your report. You need my.
No, actually, well, I like moving around, so. So thank you very much. Good afternoon. I know it's already been a long time. You've been hearing about all the things, wonderful things we would like to do and need to do. And what is clear is in order to be able to do that, you need a community who's fully on board, from accelerators, imaging, radiobiology, treatment, all of the people behind, okay? So what I was asked to do was, how do you build a community in Southeastern region for the CS facility, okay? Now, you've seen a few of these slides already, but just to say that when we are talking about from physics to medicine, I mean, this whole idea of the accelerators, does it work? Okay, doesn't matter. Okay, I didn't see it. Okay, so, you know, it started with the first cyclotron with Lawrence brother, one of the Lawrence brothers. And the reason I put this is it takes time from the idea to getting into the actual reality, okay? So the first cyclotron in 1932, Wilson already proposed what this Bragg peak you've been hearing quite a few times today in 1942, but the first patient was treated in Berkeley in 1954. And the reason I mentioned this idea of the first patient is it's not by chance the first patient was treated in Berkeley, because it happened that one of the Lawrence brothers was an accelerator physicist, and the other one was a medical doctor. And it was a collaboration from accelerators technology to medicine that led to this possibility. So I think this is really important, and this is the community we need. We need a multidisciplinary community which has expertise in a range of the topics, which makes radiation therapy, but also hadron therapy, a complicated but a really important aspect of what we are discussing. And you've already heard this from Sandro and also from Maurizio, so I don't need to say much, that actually from 1954 to 1993, all of this was being done in high energy physics laboratories, because they were the only ones who had the technology and the accelerators to do that. So the first facility dedicated 93, the first carbon facility in Japan, and then of course, you've already seen the GSI original results, which was so impressive that it led to the Heidelberg facility. And I think I don't need to tell you anything at all, other than the fact that the imaging is key. And that last caption there shows you real-time PET imaging while the patient was being treated. This was really an amazing breakthrough. And for particle therapy, if you're talking about precision and the Bragg peak, the challenge of doing real-time treatment, moving organs, compensation, and being able to get feedback is really an important issue. So I just show you, and it's interesting because you've already seen the numbers from Sandro. When I looked at this, it was 2016. We had 160,000 patients. In the last 2 years, we've gone up to 200,000 and more. And the number of facilities is also increasing. So there's a huge momentum. And I show you globally where the centers are and where they're being built, and the numbers are increasing day by day. But this one, which Sanya showed you this morning already, why we need SEEIST is because there's a huge blank area in Southeastern Europe. And this is one of the reasons, not just for the facility, but the technologies, the community, the innovation that's needed to be able to make sure we are going to start going blue or green, depending on your color, okay? So, and I wanted to say, so why do we need a SEEIST facility? One of the things is there isn't one. But what more importantly is that there are 43 million inhabitants in this region, and there is no facility. So therefore, we need to have hadron therapy access. That's an awful lot of inhabitants with no facility. The second thing is, it's been alluded to, is the region is suffering huge migration. Montenegro, by the way, as number one with minus 4.9. And Malta is taking too many of inhabitants, Nicholas, so we need to be able to reverse. No, but jokingly though, I heard the word which was, I liked very much this morning, the idea of need for brain circulation and not brain drain. So we want to train the brains, but we want them coming back, okay? So how can we try to do that? And data are difficult. And I have these data from Bosnia and Herzegovina, but actually, we don't know how accurate these numbers are, okay? And the fact is that on the other hand, it's not surprising. The breast is the most regular, and then lungs and so on. But the point is, we don't actually have really good data, as you just heard from the previous talk. So if we are talking about needing facilities, needing technologies, we need to also know what sort of numbers are we talking about and what are we going to do. So in order to, and I'm stealing your slide again, Fasna, is the fact we are not. These numbers, yes, and I know, Hans, you have the idea of incidence rates. We need incidence rates, not just the ratios. And the thing is, the problem is there's no real accurate cancer registry, and there's lots of less imaging and treatment equipment and many things to do. So what do we have to do in terms of the needs? Is let's see what building a community and having a SEEIST facility can do. And one of the things is there are more than 40 million people, as I said, who could benefit from this. There's a possibility of education, training, innovation, and capacitance building. There's cancer is, I mean, I don't think I need to tell you because you've already heard that particle therapy is a really effective cutting edge treatment. So therefore, it should be possible to make it available in the region and also to be able to join in the clinical trials Europe-wide, because one of the things is we need data and proof as to how effective particle therapy is. It will be a unique facility. You've heard this, that 50% of the time will be for research, education, training, translational research, RD trials. And we need more data because we're talking about the fact that particle therapy is really effective, but there's still a lot of research to do. It's going to be attractive for the external community as well. So rather than brain drain, you have brain exchange, and maybe some of the people will stay here. And also it's cheaper in terms of research and living costs to be here, okay? And possibility to boost the regional development and create a new generation of young scientists, innovative companies and industry, and really the idea of mitigating brain drain and reversing the brain drain in some cases. Because if you have a really attractive cutting edge center, I think we might get some of the people coming back to the region as well. And coming back to Vesna's presentation, I think what has become very important is that we need to have data gathering and data sharing in order to solidify the case, but also to see where we are going. So creating an effective cancer information and digital network, regional development, communication, handling data, but also not just networking within oncology centers in the region, but also in Europe and beyond. So being able to do all of this, effective patient selection and patient referral, and coordinated staging, follow-up, and treatment. But if we have a common electronic sharing platform, it's not for epidemiological data only, it's for many of the things that you can do. And I think the idea of the region and the country sharing this information with each other and seeing what's happening in one country, for example, Slovenia is doing really well. So it would be interesting to see what somewhere like Albania can do, for example, to be able to match and join with this. And so I wanted to say, how could we perhaps leverage the Enlight network? And Enlight was launched in 2002 following the PIM study that's been referred to earlier. And the whole idea for the Enlight network was to build a common multidisciplinary platform to be able to help each other identify challenges, share education, training, all the things we're talking about today. And you know, it's leveraging the spirit of physics collaboration philosophy into the multidisciplinary field. So this has been now existing for a number of years. And we have annual meetings, which are open, free in this normal way we work. And it's networking, it's building bridges, it's raising awareness, and also sessions on education and training as well. So I think that this is totally open to the community, but also to have the meetings here that would perhaps be the most effective. But as it happens, the next, so it's one of the training days, because last year we had the meeting in London. This year we had it in Caen. So Jack Palloso is there who organized the training. And this training is for students, but also professionals who would like to hear what's happening in the other fields. And the idea of Enlight is really with the patient in the middle, bringing all aspects of imaging, financing, hospitals, industry, with the idea that the patient gets the best treatment. So that's the motivation by the Enlight network. Oops. And then, so what do we do now for the next steps in terms of a community? You've already heard about history and design study, etc., but it's just from our community point of view, preparing the cost action, which we have just actually prepared and submitted recently, 6th of September. Building an epidemiological platform which can be shared and trying to define the data Vesna was talking about that we are missing. There is a Marie Curie call out in January, so we will submit this. In the HITRI, there's a work package too, which I'm leading together with Mimosa, also with the Montenegro Oncology Clinic, to try to see how we can also leverage this. And ensuring that the C region is represented in the 2020 Bergen Enlight meeting, and then maybe the following year having one in the region, I think is really important. And I think while we are doing all of this, we need to raise the role of SEEIST and the activities using any of the communication platforms in order to be able to secure not only more funding, but get more people interested in this project, particularly the people who are outside the region, but come from the region. It would be very interesting. And so talking of Maurizio's theme of planting and growing trees, I'm not as into a big tree yet, just a flower. And the idea of this flower is we need all the petals. Okay, so this is really the membership of the cost proposal that went in, and the petals must contain all of the people in the region as well as the other leaders, so we can work together to make a flower at least. Tree maybe in a few years from now, okay? And so I've told about the future possibilities. So they really, from my perspective, the urgent needs are a multidisciplinary network, build on existing networks rather than starting something new, bringing in existing facilities, raising awareness, I think is really important of heart-rhythm therapy in the region, is really important. Integration, common cloud platform, open access, training next generation, I mean, all the things we've discussed. But I think also it's a multi-stakeholder, shareholder a network, including industry, public bodies, and ministries of health, and not just research. So I think this is my feeling of with being in light that what are the things we need to be able to build a community so that when we have a center, but even before we have a center, that we have people who are trained, who are interested, who are involved. So we have the researchers as well as the users. So thank you.
Manjit works since long time on this question of Enlight and the community building. We have 4 more speakers, and it's just a coffee break we can use for it on the agenda. I propose we can do this, but the next speakers then have only 15 minutes or 10 minutes if possible. So we have here another speech on Mr. Yamamoto. Is not. Ah, okay, you are coming. Sorry, I didn't see you in the. You have a. Thank you.
Thank you very much, Chairperson, and good afternoon, ladies and gentlemen. Thank you very much for giving the IAEA to make a presentation this afternoon. I would like to give an overview of the IAEA Technical Cooperation Program for Capacity Building in the SEEIST project. The TC program, the IAEA's TC program, abides by a number of key principles, as outlined on this slide. The program contributes to development goals while responding to member states' needs, and member states must undertake to use the technologies for peaceful use only, in a safe and secure manner. Member states drive the program and share responsibility for it, and TC support its availability. Support is available to all member states without any discrimination. The program depends on cooperation among member states and with partners, and aims to be as transparent as possible. The IAEA has a long history of supporting member states in capacity building under the TC program framework to ensure the effectiveness and sustainability, as well as safety of the infrastructure. The training opportunities will be arranged to fellowships or scientific visitors to already existing centers to get their experience and knowledge shared by qualified experts. The Technical Cooperation Program of the IAEA, the primary mechanism for our implementation is to serve member states. It builds national capacity in peaceful applications of nuclear science and technology. The program also facilitates networking and knowledge sharing, and very importantly, the development of suitable partnerships at all levels. The main mechanism the TC program uses are provision of training, expertise, and in some cases procurement, as listed in this slide. We may also organize such as workshops to provide the experts to share their knowledges. The program is guided by requests for assistance by member states in accordance with the national project or regional project priorities, and provides guidance to member states on the best way to address their needs using nuclear technology. As in many other development-oriented programs, the TC program cycle consists of program planning and approval, program implementation phase, and program review phase. And needless to say, we have many partners, and each stakeholders play a different role in project, implementing the project and achieving the result of the project. The TC program cycle consists of a preparation period and implementation, which comes hand in hand. Normally, the preparation period consists of 2 years, and most of the TC projects are 2 years or 4 years cycle in duration. Now, this is the whole process of IAES project design phase. Also for the IAES regional project to support SEEIST, we have started our preparation already in May 2008 when we received the concept from the SEEIST member state. We went through several steps of designing phase, including some clearing process, review, and currently we have finalized the regional project design and waiting for the Board of Governors approval in November 2019. I would like to touch upon the design of the IAES regional program project related to the SEEIST. The title of the project is Developing Human Resource for Setting Up an Ion Beam Therapy Center within the joint Southeast European International Institute for Sustainable Technologies. And objective is to build critical mass of human resources initially needed for the merits of the emerging hadron tumor therapy and research facility. And the listed countries are the member states of the IAEA TC Europe region, which will be considered as potential possible member states to participate in this regional project. Now, within this project, the main objective is to provide capacity building support by training of scientists, medical practitioners, engineers in various specialized, and people in various specialized fields, as well as to support networking opportunities by those relevant stakeholders who will be involved in the project. The expected outcome of this project is to achieve critical mass of staff for construction and operation of the hadron tumor therapy facility. And in order to achieve this, the expected output will be, first, the qualified staff, which could be medical physicists, engineers, technical staff, for construction and operation of hadron therapy facility becomes available. In order to do this, we have relevant activities, which is to train the engineers and medical physicists in relation to the establishment of the hadron therapy facility. The second expected output is to improve knowledge among stakeholders and awareness raised on hadron therapy among SEEIST stakeholders. In order to achieve this output, the expected activities could be the training on knowledge of hadron therapy technologies and related applications for relevant stakeholders. And the third expected output is transfer of knowledge of Southeast European research. And in order to achieve this output, the planned activities could be promoting networking among scientists. Now, in order to implement the mentioned activities, what we, under the project, intend to implement would be to organize fellowships for engineers, medical physicists, and many others as needed. And also to organize workshops for stakeholders to deepen their understanding about the therapy center or technologies or expected institutions. And also possibility is to organize a group scientific visit of experts to visit other institutions to learn from them or exchange views. The project is designed in a way that depending on the progress of your main project, we can, in a flexible manner, apply the requested needs, respond to the requested needs, and implement the activities or inputs based within the framework of the IAEA methodologies and framework. And currently, the project is designed for 4 years, and we have budgeted 500,000 euro for this project. Currently, it is going to be approved by the Board of Governors as a footnote A, which means once the project is approved, and also depending on the progress of your main project, we will allocate the necessary funding in order to respond to the required needs, such as to organize fellowships, workshops, or a group scientific visit. I think my presentation is scientifically the least interesting for the audience, but I hope this has given you some kind of overview of the activities of the IAEA. Thank you very much.
And we are confident that the approval will be given, and then everything will move automatically in connection with the SEEIST project. So thank you very much, because this is something which is real support which we need. Thank you.